I bought a green screen. Huh. Hello, my name is Ethan and welcome back to my channel. This is part 2 of my second Nerf turret, so I'd recommend checking out my previous video. In this video, I'll be talking about the turret electronics, the pan and the tilt, the base, the dart loader, and I'll end with tying everything else together. Let's get started. But first, I'd like to thank PCBWay for sponsoring this video. PCBWay is a manufacturing company based in China who provides many services, including CNC machining, 3D printing, sheet metal fabrication, injection molding, and of course, PCB manufacturing and assembly. The ordering process for these PCBs was very simple and the boards arrived surprisingly quick. Thanks PCBWay. Anyway, back to the video. To get rid of the rat's nest I left off with, I had to design a circuit board. I started by roughly laying out the components in CAD and then cut out a dummy board. Once I had everything laid out the way I wanted, I got to work on the circuit design and sent the files off to PCBWay. To save space on the board, I used some very small surface mount resistors. I didn't realize how small these things were until I had them right in front of me. Getting them soldered wasn't too difficult, and the end result wasn't too bad. After that, I got to work soldering everything else. The components didn't change much from my last video. I'm still using the same DC motor controller, logic level shifter, and voltage converters. I did switch from a Raspberry Pi Pico to the Adafruit Itsy Bitsy to save on space. I got to work connecting everything so I could test the board. The 3 magazine switches worked just fine, but this dart sensor for some reason wasn't. Turns out I had the sensor input wired with a pull-down resistor instead of a pull-up. A digital input on a microcontroller should be either clearly high or low. When you apply voltage to an input pin using something like a button, it becomes high. However, when you remove the voltage, the input enters a floating or undefined state that can be easily affected by outside influences. A resistor can be added between the input and ground, pulling the undefined state down. This is called a pull-down resistor. A pull-up resistor does the opposite by connecting the input pin to whatever voltage is high. To swap from a pull-down resistor to a pull-up, all I had to do was cut the trace and solder a new one on. My first turret had a couple of issues that I wanted to address. The pan mechanism had some backlash due to gaps, the turret was mounted directly to thin, brittle acrylic, and the wires had to take a strange route to the base. The solution to all of those issues was this belt-driven design. The servos are tied directly to what they're driving, the hollow shafts allow the wires to easily pass through, and the design is much more solid. As I was testing the whole thing for the first time, I got a little carried away. Surprisingly, these were the only 2 things that ended up breaking. Once I gave it a proper base, it was able to not fling itself off of my table. As you may have noticed by how much the whole thing moves, the turret's weight and weight distribution are problematic. My previous turret only weighed 370 grams and its weight is nicely centered on the tilt axis. This new design weighs almost double at 610 grams and its center of gravity sits entirely above the tilt axis. This servo is more than capable of slinging that weight around, but it shakes the whole thing quite a bit and can cause the belt to skip. I'm a bit too far into the design process to address those issues, so I'm just going to ignore it and hope it doesn't become an issue later. My initial plan for my first turret was to manually load each dart. So when I decided to add the dart loading later, I had to really cram in the extra components. The additional 6 sensors, 3 servos, and 2 motors needed a bunch of extra wires, and they really crowded the breadboard. The new wires passed through poorly placed holes that made assembly difficult. The pins on the breadboard were all unlabeled, and the arming hook ended up blocking access to the USB port. I got around that by adding this door, but it was still a pain to program. I didn't want any of that for version 2, so I did some more careful planning and didn't let myself add anything extra. I started with basically the same size base. I went with the smaller microcontroller and increased the battery size for the very power-hungry motors. The new pan and tilt design took up more space than the old one, and so did the dart loader. Once I finished adding the power switch, power distribution board, and DC converters, I was left with this much space for everything else. I was able to fit everything I needed on these 2 stackable PCBs. The bottom one has a Raspberry Pi Pico and 2 DC motor controllers for the dart loaders. The top PCB has a 5-volt converter, an analog to digital converter for the dart loader sensors, connectors for power, servos, dart loader motors, dart loader sensors, turret communication, and the display. The 2 PCBs stack on top of each other and fit quite nicely in the base. And would you look at that, the USB port is easy to get to. I was planning on using the same display and buttons as my first turret, but I only had 1 input left on the Pico. I ended up getting this cool display from Pimeroni that is controlled by a dedicated Pico. It's got 4 buttons and can connect through I2C. The dart loading on my last turret was very slow, taking around 30 seconds to load a dart. With the new dart loader, I had 3 goals. Load the magazine as quickly as possible, load the magazine all at once, and have the design be compact. To be able to push the darts as far as I needed and still have a compact design, I knew I needed something that telescoped. My mind immediately went to this hand-cranked lift that's at my work. It's got a fixed base, the main forks, and a center floating frame quite similar to a drawer slider. The lift extends using pulleys, so that's what I went with. My first iteration used small rollers that only kind of worked. The wheels didn't roll very well and the whole thing was incredibly flimsy. I switched to some steel rods and the whole thing was much more smooth and much more rigid. The next step was to figure out how to quickly pull the string to extend the darts. I thought of the spring used for tape measures, so I took apart this miniature one and got to work. The initial testing went alright, but the string tended to get stuck underneath the spring. Untangling it and putting it back together was also a pain, but the biggest issue was how the layers of the metal would unwind. When you pull on the metal, it coils tightly, so when you release it, all the layers have to slide on top of each other to unravel. Sometimes it would unravel quickly as expected and without a problem, but other times it would stay wound up. The next step was to take apart a larger tape measure to see how it worked. The key difference with this larger tape measure was how the metal coiled when you pulled on it. The layers separate as you pull the tape out instead of coiling tighter, which allows the spring to retract much more reliably. I applied this idea to my spool and it worked like a charm. Over time, the carriages didn't move quite as smooth as before, so I added this extra set of pulleys just to get that much more force. Fast forward a month or 2 later, I had to get a new ID badge at work and was given this handy badge retractor. All that work just to end up reinventing the wheel. With the dart pusher moving, I needed a way of pulling it back down and quickly releasing it. I decided to use a motor and a spool of fishing line to pull it down. For a quick release, the spool needed to quickly unwind. To do that, I separated the spool from the drive motor and used a second motor to push and pull the spool. To pull the dart pusher down, the spool is pushed into the drive motor, winding the fishing line and pulling it down. To extend, the spool is pulled away from the drive motor, allowing the spring and pulley system to fully extend the pusher. To automate the process, the microcontroller needs to know where the pusher is and when to turn each of the motors on or off. To do that, I basically turn the whole thing into a switch. When retracted, current travels from here through these wires and then into one of the microcontroller's inputs. It's the same idea when extended. Current travels from here, through these wires, and then into a different input. The circuit is made up of solid core wire soldered to spring-loaded pogo pins. To pull the carriage down, both motors start spinning up. As soon as the spool engages with the drive motor, the carriage starts moving and breaks a circuit, letting the microcontroller know to turn the clutch motor off. The drive motor keeps spinning until the carriage moves all the way to the bottom and completes the lower circuit, stopping the drive motor. To release the carriage, the clutch motor starts pulling the spool away from the drive motor. Once the carriage breaks the lower circuit, the clutch motor runs for another 1/10 of a second before stopping. The next part was designing the tilt mechanism. I used 2 servos, one to pivot the dart loader and one to move the pivot point. This allows the dart loader to get close enough to push darts into the magazine and far enough to get out of the way of the turret. It also has the added bonus of taking up less space.
A lot of people in the room, you need more space. Voila, right into the wall. Wow.
The last feature to add was dart sensors. My last turret used an IR LED and IR sensor, so I went down that path. One thing about this setup is that these LEDs can't be too close to the darts or the receiver wouldn't see any of the reflected. I tried recording a clip backing up what I had just said, but for some reason the receiver had no problem seeing the reflected light. I don't remember how I came to that conclusion, but let's just pretend that it's true. Anyways, back to the video. To get the right distance from the darts, the LEDs would need to stick out this far, which would interfere with the base. I had to angle the LEDs to maintain the proper distance and prevent interference. I added the LEDs to the dart loader and soldered them to the circuit board. Assembly wasn't too bad, but I just hope I never have to replace any of the LEDs. Now that I had all the individual parts of the system working, I had to tie it all together. All of the controls are split between various microcontrollers in the base and the turret. This one controls the display, this one is the master and controls the dart loader and communications, this one controls the firing components, and the OpenMV camera tracks things and controls the servos. They're all connected together using different 2-wire communication protocols. The 2 picos and the itsy bitsy are connected on the same I2C bus, the main pico is connected to the camera using UART, and the camera and itsy bitsy are connected with basic I/O signals, each with one input and one output. I2C, short for Inter-Integrated Circuit, is a serial communication protocol used for connecting as many as 128 devices through just 2 wires. The master device sends address data packets to specific devices it needs to communicate with, which then send data packets back. UART is another 2-wire serial communication protocol that stands for Universal Asynchronous Receiver Transmitter. It is a very simple protocol that connects only 2 devices together. Data is transmitted from the transmitter pin of one device into the receiver of the other device, and vice versa. During operation, the master will constantly ping each device for various bits of information. It will ask the display if the user wants to start the turret, ask the turret if the magazine has darts, and then will tell the camera to start moving. Once running, the camera will constantly scan for targets and tell the turret to fire once a target is centered. Or at least that's the idea. To start, I went as basic as I could and tried to get the base and the display to talk to each other. The first bit of code I ran was supposed to find any device on the I2C bus. All I got was a long list of random addresses, none of which was the address I was looking for. After a bit of digging, I discovered that each I2C line needs pull-up resistors to the supply voltage. The typical resistance value is between 4.7K and 10K. At this point, I was on a family trip and didn't have my variety pack of resistors, so I stole the 10K resistors from the dart loader. The 10K resistors didn't work, so I removed the other 10K resistors and soldered them in parallel to bring the resistance down to 5K. Worked like a charm. With the communication working, I began connecting the microcontrollers together, starting with the camera and the turret. At first things started off fine, but when the motor spun up, the servo started to move erratically. A look on the oscilloscope revealed that the servo signal was getting tons of noise when the motor ran, so instead of addressing the noise, I just turned off the PWM signal right before turning the motors on. You can't drown out a signal with noise if there is no signal. In that process, I accidentally told the pan servo to extend past its limit and ended up breaking it. This started an unfortunate avalanche of broken hopes, dreams, and parts. I did some more testing and broke the DC motor controller on the turret. I don't really know what broke it, but I'm guessing it had something to do with all of that. Desoldering and replacing the controller was such a joy. I didn't have any luck with the solder pump, so I used solder wick instead. I replaced the board and hoped I wouldn't need to do that again. Once I had the two turret controllers talking to each other, I added the base Pico to the mix. The communication between all three controllers worked until the motor started spinning. The motor noise would disrupt the I2C lines enough to stop any communications. At this point, I realized I had to actually address the motor noise. When messing around with some capacitors in an effort to absorb that electrical noise, I shorted something and broke the microcontroller on the turret. Or at least I think that's how it broke. In any case, this chip ain't supposed to get that hot. I spent an hour and a half trying to wick away all the solder keeping this board in place. But just a few stubborn pins were preventing the board from coming off. After a bit, I just gave up and cut it out with a Dremel tool. Resoldering went much better. I also managed to burn this trace completely off the board. Once I fixed that, I decided to just completely isolate the motors from the rest of the components. To do that, I decided to use two separate batteries, one just for the motors and another for everything else. To bridge the two circuits together, I'll be using this little chip called an optocoupler. One side of the chip has an LED and the other side has a light-sensitive transistor. The PWM signal from the microcontroller will be fed into the LED side of the chip, and the transistor output will connect to the motor controllers. Since the two circuits aren't electrically connected, no amount of voltage spikes from the motors will make its way back to the rest of the turret. I made a blank PCB to test fit parts, planned out the traces, and then milled out the PCB myself because I was too impatient to wait more than a week. I removed the components from the test PCB and soldered them onto the new one. Almost looks like it was always supposed to be there. I powered everything up only to find out that it didn't work. Of course, I quickly jumped to the conclusion that the output signal should be 5 volts instead of the 3 volts I had been successfully using this entire time. I stole a 5 volt converter from a different project and soldered it to the circuit board, which also didn't work. Turns out all I needed to do was recalibrate the speed controllers. Once calibrated, I started testing the motors. It didn't take long before the motors started to sound weird. Not long after that, the circuit board broke, followed by the 5 volt converter. I soldered some new traces on the circuit board and put the 3 volt converter back on. And of course, since I didn't actually fix anything, I broke the 3 volt converter too. That thing just sparked. I was getting sick of breaking components on my circuit boards, so I went back to the breadboard. I hooked up a Pico, optocoupler, DC converter, a speed controller, and a motor. I'm using the same speed controller, but this time I left the capacitor on that came with it. I hooked up 3 channels on my oscilloscope. The green line is measuring the 3 volt output from the DC converter, the yellow line is measuring the PWM signal on the motor side, and the purple line is measuring the voltage directly from the battery. As you can see, the motor hardly affects the signal or the 3 volts. The battery voltage does get some spikes, but it's very minimal and only briefly adds an extra 2 volts on top of the 16 from the battery. I removed the capacitor to match what the actual turret setup is like, and the difference was quite substantial. The voltage spikes were consistently adding 4 volts on top of the battery 16, with peaks adding more than 12 volts. I kept the motor running until the DC converter failed in exactly the same way as last time. The failure happened right at the voltage input into this chip, which has a maximum 28 volt input. Back to the turret, I measured the same voltages to confirm the noise I was seeing with the breadboard. I lost the original capacitors for these speed controllers, so I ordered a single large one. I soldered the ridiculously large capacitor to the circuit, and sure enough, it got rid of all those problematic voltage spikes. I put everything back together, tested the clearance, and did some dry fire tests. You're probably wondering what kind of idiot would remove such an important capacitor. It's me. I'm that kind of idiot. I never put the capacitors back on because there just wasn't space. Anyway, I replaced the dart loader resistors I had taken earlier and started testing the IR sensors. For some reason, the output was much lower than it should have been. I almost left it, but I figured at least one part of this project should work well. I went back to the breadboard for some testing and hooked up the LEDs exactly as I had on the loader. As is, the voltage measurements only get up to 30 millivolts. I realized the IR receiver was backwards, so I flipped it. The output was much higher. And you know what that means? Another round of desoldering! I got the board off, took out the LEDs, put some new ones in the correct orientation this time, and soldered it back together. Naturally, one of the sensors wasn't working at all. A closer look showed that the LED wasn't powered on. I took some voltage measurements to see if the LED was getting any power and noticed that one of the traces had been cut. Once I got that fixed, everything was working as expected. When I started to program the positions for the servos, one of the servos wasn't responding. Turns out the PWM signal coming from the Pico was 0.2 volts instead of the normal 3. I switched the servo to another pin so I wouldn't have to replace yet another microcontroller. Next, I started to define the pan and tilt servo limits. I didn't design any method of belt tensioning for the tilt, so when the cheap belt started stretching, the belt started skipping. I started brainstorming ways to incorporate a belt tensioner into my design. At first I was feeling real lazy and just zip tied the belt. It worked surprisingly well, but it was a bit too janky for my taste. I ended up zip tying some bearings to it and it worked well enough. The very last thing standing in the way was the communication between all the microcontrollers. I started running a simple program to exchange bits of data between everything, but the I2C communication wasn't working at all. By this point, I was getting really tired of issues, so I decided to simplify the communication. I got rid of the display and reprogrammed the I2C pins to be regular I/O pins. The turret and base will basically just play tag when they need to work together for the dart loading process. When testing the changes, I noticed that a second pin on the base Pico was broken, which explains why the I2C wasn't working earlier. I really didn't want to replace the Pico, so I cut the trace from the broken pin and soldered a wire from the last remaining I/O pin to it. After fixing a few simple problems, I finally got the whole thing to work. I hope you enjoyed this video as much as I enjoyed making it. So see you in the next one. All right, how do we get out of here? Are you good?
Yeah, that's good.
Don't lie.
Okay, that honestly looked like shit. Just you.
Okay, tell the truth. Lie, please lie a lot.
Easy. Take it easy.